And good morning, everybody. Welcome back to Top 3. Special welcome to our visitors for today. Plan for today is I have a quiz for you on Standard 13, and then we are going to discuss Standard 14, standard on Lagrange multipliers and constraint optimization. I had to watch a video on for today. I've got my usual office hours for the next couple days, this afternoon from 2 to 3, tomorrow morning from 10 to 11, and tomorrow afternoon from 1 to 2. As far as homework goes, we will have a quiz on Friday over Standard 14, and then Monday's going to be the next exam over Standards 1 through 14. Standard exam rules will apply. You can bring in one sheet of notes, front and back, for that exam. And like I said in the email, unfortunately, we're running behind where I was hoping to be at this point in the semester due to me being sick, and things just going a little bit slower than I was hoping for. And so, I had to rearrange some of the standards. I'm combining two standards into one with 15 and 17. The original 15 and 17 are now just the new 15. I did cut a couple standards off at the end, and so now we're only going to have 17 standards in total. If you look on the syllabus, I reflected what you need to get. I changed what you need to get each final grade to reflect that. Does anybody have any questions or comments before we get started for today? So, several people are asked one day, what is 2 times 2? The engineer whips out his graphing calculator, presses a bunch of buttons, and finally says, 2 times 2 is 3.99 plus or minus 0.01. The physicist consults her technical references, sets up the problem on her computer, and says, 2 times 2 is somewhere between 3.98 and 4.02. The mathematician thinks about it for a second and says, I don't know the answer to that, but I do have a proof that an answer exists. The philosopher smiles and asks, what do you mean by 2 times 2? The sociologist says, I don't know, but it sure was nice talking about it. The biologist says 2 times 2 is a polygamous mating system. And finally, the medical student says plainly, 2 times 2 is 4. The others all look at her astonished. When they ask her how she knew that, she says, oh, simple, I memorized it. All right, and with that, it is time for today's quiz. So I'm going to go ahead and pass this out. One, two. Not sure if I have any extras. If I do, I'll pass a couple.
I was going to say, if you have extras, we'd like them. Thanks.
Let me see how far I get with the... Okay, good, because that's the last section.
All right.
So a couple comments on this quiz. You notice this is kind of one of these problems like we had in Standard 13, find the absolute max and min on compact set. You do not actually need to find the absolute max and min. You just need to find all the points that the extreme value theorem says could be the locations of absolute maxes and mins. Meaning you don't have to do the step at the end where you plug them all into a table. I'm okay with you skipping that.
Excuse me. Do you have a pencil you can borrow, Angels?
Yes.
Thank you.
Feel free to use the back of the quiz if you need some extra room. I know this one's probably a bit tight. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Thank you. Oops, sorry. Don't want to give it to me. Thank you. Alrighty. So, standard 14. We're looking at the process of constrained optimization. Where, if you recall, the theorem from the video says that if you have two functions, f and g, going from Rn to R that are C1, meaning they're differentiable everywhere, and their derivatives are all continuous. If we look at the set of points where g of x is equal to some fixed constant c, for this right here, by the way, we call the constraint equation. And if we only cared about looking at the set of points where g of x is c, and we want to say, on this set of points, how big or how small can the function f get, meaning f restricted to this set S of points satisfying the constraint equation, we said that if f has restricted to S has an absolute max or min at a point A, one of two things has to happen. Either the gradient of g is going to be 0 at that point A, meaning all the partial derivatives of g come out to 0, or the gradient of f and the gradient of g are scalar multiples of each other. Meaning there's some scalar value lambda, which we call a Lagrange multiplier, such that the gradient of f is equal to lambda times the gradient of g at that point A. And we looked at an example where we looked at how can we maximize or minimize a function f. I think the function was x squared plus y, subject to the constraint where x squared plus 2y squared had to equal 1. And what I'd like to do today is to look at a couple more examples of constrained optimization where we're given some problem, we have to kind of set up our f and our g, and we're ultimately looking to use the method of Lagrange multipliers to find absolute maxes and mins. So the question I'm going to look at is we have an open rectangular box. Must have a fixed volume of 4 cubic feet. So, question we're looking at, we've got this box, and the fact that it's open means that box just doesn't have a lid to it. But we have a rectangular box. I'm going to call its height h, its width w, and its length l. And we want to force that this box has to have a volume of 4 cubic feet. And the question is, what dimensions should the box have to minimize its surface area? So if you were like a construction company, like maybe, I don't know, you worked at UPS or something, this might be the sort of thing you might be interested in. How can I construct a box such that it holds 4 cubic feet of material inside of it, but I want to minimize the surface area of that box in order to minimize, say, the cost and, or the amount of material that's needed to make that box. And so, if we look at this, we sort of have these 3 variables that correspond to the dimensions of the box: height, width, and length. We're given a constraint, the fact that the box needs to have a volume of 4 cubic feet. And we're asked to minimize something, namely the surface area of the box. And so what I'd like to do is to be able to set up a couple of functions, f and g. I think that'll be going from R3 to R3 because we have 3 sort of unknown variables here. And ultimately, I'd like to take this word problem and translate it into this sort of problem, where we're given a function f subject to a constraint that we'd like to minimize in this case. So what do y'all think about this? First of all, I'd like to find formulas for what f and g might be. We know something, first of all, about the volume of this box, that it should be equal to 4 cubic feet. In terms of h, w, and l, the height, width, and length of the box, how can we find a formula for the volume using those 3 variables? Yeah?
Multiply them all together, so height times width times length equals volume.
Yeah, it's a rectangular box, so the volume should just be multiplied height times width times length. And according to the problem statement, this should be equal to 4 cubic feet. So the other expression we'd like to be able to find is what should the surface area of this box be in terms of h, w, and l. This one's going to be a little bit more complicated because our box is going to have 5 sides, kind of the left and right sides, the front and back, and the bottom of the box, but not the top because the top's open. So for surface area, we need to have the surface area of the front and back plus the surface area of the 2 sides, the left and right sides, plus the area of the bottom of the box. Let's see. Polly, what's going to be the area of the front and back of the box?
So it should be 2HW plus 2HL.
Okay, so you're doing the, okay, you want to go ahead and do the left and right sides as well. Yeah, I would agree. I think the front and back of the box are each going to be rectangles with height of the h, width of w. So the front and back of the box are going to each have an area of h times w, which if we combine will give us 2hw. And then you went ahead and found the left and right sides as well. Those are going to be rectangles with dimensions L by h. And so the sides are each going to have an area of h times L. So combine to get 2HL. And then how about the area of the bottom of the box? Width times length. Except this one is only going to be a single copy of W times L because we are including the bottom of the box but not the top of the box. That doesn't count towards the surface area since it's an open box. I don't know, if you're working for UPS, you might want to be able to close your boxes, but for the purposes of this problem, we're assuming you don't. So here we have two different expressions. We have an expression for volume, just being H times W times L. We have an expression for surface area, 2HW plus 2HL plus W times L. And ultimately, what we'd like to do is we want to minimize surface area if the volume is 4 cubic feet. So if you look at the theorem, which of these two formulas do you think is going to be our F and which is going to be our G? Jacob?
F is probably the surface area, and our constraint is the volume.
Okay, why is F going to be surface area?
Well, it's not equal to anything.
Yeah, that's the expression we're trying to minimize. We want to minimize our surface area. So the function that we want to minimize is going to be our F here. So this is going to be F of H, comma, W, comma, L. It's going to be a function that takes in three variables, height, width, and length, and spits out the surface area. And then I think I agree, Jacob, that I think the volume is going to be our function G, and our constraint that we're given is going to be that G of H, comma, W, comma, L is going to be equal to 4, corresponding to the fact that we're given in the problem we only care about boxes whose volume comes out to 4 cubic feet. If we didn't have this constraint on G, I would say F doesn't have to have an absolute max or an absolute min, because we could just make H, W, and or L as big or small as we would want, and make this expression as big or small as we want. But the fact that volume has to come out to 4 is going to restrict how big or small we can make our H, W, and L respectively. And so now, this is the sort of problem we looked at in the video, where we're given an F that we'd like to find the absolute min of, subject to the constraint G of X. In this case, G of height, width, and length is equal to the constant value 4. So, what do we want to do with this? What would be, according to the theorem, how can we check to find points where we could potentially have an absolute max or an absolute min for our surface area function? Yeah?
We can find the gradients of both G of HWL and F of HWL.
Sounds pretty reasonable to me. The points, in order to find points where we could have an absolute min for F, we're going to need to know where's the gradient of G0, or where's the gradient of F, a scalar multiple of the gradient of G. So I agree. I think it would be useful to know what the gradient of F and G are. So the gradient of F, in this case, is going to be del F del H, comma, del F del W, comma, del F del L. If F is just equal to H times W times L, Jackson, what's going to be our del F del H here? Yep, yep, we get constant times H, WL times H, so the derivative of that will just be WL. Benu, how about our del F del W? If we were to differentiate, I'm sorry, I'm doing del F del G, or the gradient of G. Jackson, you confused me. Let's do gradient of G first, because that's what I've already have written down. Okay, sorry. Benu, can you tell me what the gradient of this function is, with, or the derivative of our volume function with respect to W?
HL.
It's going to be H times L. Watch it. And finally, Jack, how about our del G del L here?
HW.
It's going to give us H times W. So that's going to be our gradient of G, not of F. And now, if we want our gradient of F, now we can take del F del H, del F del W, and del F del L. John, what's our del F del H going to be?
2W plus 2L.
2W plus 2L. Laurie, how about our del F del W? 2H plus a single L. And Avery, how about del F del L? 2H plus W. Okay, so now we have our gradients. We know what our gradient of G and our gradient of F are. And so now, I think we can look through each of these two conditions and find where is the gradient going to be 0 and where is the gradient of F going to be a scalar multiple of the gradient of G. So let's see if we can find that out. Let's start by finding where's the gradient of G going to be 0. So if we set the gradient of G to be equal to 0, meaning the 0 vector, that's going to give us a system of equations where W times L has to be 0, H times L has to be 0, and where H times W is equal to 0. If we wanted to solve this system of equations, what would need to happen here in order for width times length, and height times width to all come out to 0? Stop.
At least 2 of them have to equal 0.
Yeah, we would need at least 2 of our variables, potentially all 3, but not necessarily, would have to come out to 0. Is that something that can happen in this scenario? Emily, I see you shaking your head. We're talking about what?
A box.
Why can't we have an infinitely small box? Sure. What if our box is a single point? Wouldn't be a very practical box, but it still exists. It could still theoretically. All right. Change of plan. Let's say we were given this G and F, and we didn't know that they had to correspond to some real-world thing like a box. Is this something that can still happen in our constrained optimization problem? Avery? Yeah. I think you're absolutely right, Emily. In a real-world scenario, this can't happen because we want an actual box. H, W, and L all need to be positive numbers. But even if we're ignoring that sort of real-world constraint, so to speak, we're still going to be operating under the constraint where the volume, meaning H times W times L, we're assuming has to come out to 4 cubic feet. And I would argue that if any 2 of these variables, in fact, if any one of these 3 variables was 0, that would be impossible. That if any one of these 3 variables is 0, height times width times length would come out to 4, or would come out to 0 instead of 4. And so this is impossible if our constraint is to hold. So this can't happen if our constraint height times width times length equals 4 is satisfied. And so what does that mean? That's ultimately going to mean case number 1 here isn't going to give us any points to work with. We're not going to be able to find any points where the gradient of g is 0 and that are also points that satisfy our constraint equation, that volume equals 4. If our volume is 4, it's impossible for the gradient of the volume function to come out to be 0. And so we're just not going to get any potential points from this first condition. Any potential points we find would have to come from the second condition here. We stop for just a second and see any questions or comments so far. So now we need to look at this second constraint, or the second possibility, which is that if we have a critical point, it could be where the gradient of f and the gradient of g are going to be equal to each other. And so if we look at that, where gradient of f is lambda times the gradient of g, what we're going to find is that we'll get that 2w plus 2l, comma 2h plus l, comma 2h plus w is going to have to be equal to lambda times wl, comma hl, comma hw, which we can actually write out using a system of equations, where the first equation is going to be 2w plus 2l is going to be equal to lambda times wl, where I just took the first components of each of these vectors and set them equal to each other. What's going to be one of the other kind of equations in our system of equations this would give us? In particular, if we were to set the second coordinates of our vectors equal to each other, what would that end up giving us? Oh?
Lambda HL equals
2h plus l equals lambda times hl. I like it. I wrote it in the opposite order of what you said, just so it matches up with the first one, but it doesn't really matter. And finally, how about our third equation? Yeah?
2h plus w equals lambda HL.
Equals lambda
Sorry,
times
HW.
hw. I like it. All right, so now we end up with this lovely looking system of equations that we need to solve, where we have w's, l's, h's, and lambdas. Golly. One doesn't look as nice as the example the other day. So here's a trick. If you have a sort of nasty system of equations like this that you need to solve, find out which variable shows up in all of your equations. Because if you look at all these three equations, there's only a single variable that's going to show up in all three of them. Which variable is showing up in all three of these? Emily? Lambda. First one doesn't have H, second one doesn't have W, third one doesn't have L, but all three of them do have lambda shown up. So what we can do is we're going to rewrite each of these three equations in terms of the variable lambda. And if we do that, we can actually rewrite this first equation. Instead of being 2w plus 2l equals lambda times wl, if we solve that first one for lambda, we can write it as lambda equals 2w plus 2l all over w times l. Just take this first equation, divide both sides of it by w times l. How about our second equation? If we were to take this second equation here and just solve for lambda to get lambda by itself, what would we get that lambda is going to be equal to? Let's get some more of the class involved. Olivia.
Lambda would be equal to 2h plus L divided by HL.
I agree. Just divide both sides by HL, and we can get lambda by itself in the second equation. And finally, how about in our third equation? Gary, do you want to give this one a try?
The lambda equals 2h plus w over w.
All over HW. I like it. So we can rewrite our system of equations to be a little bit nicer by just say solving all of them for lambda. And now we can just set each of these three expressions equal to each other. Because if they're all equal to lambda, they should be equal to each other. And turns out if we rewrite these a little bit nicer, we can actually make these look a little, we can actually rewrite these in a way that's going to make it a little bit easier to find relationships between HW and L respectively. So for this first one, for instance, we could write it as 2W over WL plus 2L over WL, which is going to be the same as 2 over L plus 2 over W. We can rewrite the second equation as 2H over HL plus L over HL. And Sarah, how's that going to simplify?
That's going to be 2 over L and 1 over H.
Plus 1 over H. I like it. And the bottom one, we can write as 2H over HW plus W over HW, which is, what, IX? How can we simplify these two fractions?
It's going to be 2 over W plus 1 over H.
2 over W plus 1 over H. I like it. And instead of trying to set all three of these expressions equal to each other, I think we might have a little bit of an easier time if we take these three. It never ceases to startle me when I'm trying to draw something on the board and my chalk breaks in half in the middle of it. We take these three expressions and set them all equal to each other. See what we can find out about W, H, and L. Let's fix this. So we're going to write up, so we need that G of HWL is H times L times W equals 4 still. I'm going to keep that up on the board because we're not done with it yet. But let's see what happens if we take these two expressions and set them equal to each other. Because they both equal lambda in a critical point, so they have to equal each other. So let's see what happens here. We take 2 over L plus 2 over W and set that equal to 2 over L plus 1 over H. If we wanted to write one of our variables in terms of another one, what could we do with this equation? Is there anything we can, any way that we could simplify it? Yeah?
Subtract 2 over L from both sides.
Okay, both sides have a 2 over L showing up, so that'll give us 2 over W equals 1 over H. Jackson? Ooh, okay. Tell us that W over 2 equals H over 1. I like it. What I was going to suggest is we cross multiply to get 2H equals W, but that'll give us the same thing. And if we cross multiply here, we will get 2h equals w. Or using Jackson's method, w over 2 equals h. Really the same equation, just written slightly differently. So this is telling us something, that if we have a critical point where the gradient of f is a scalar multiple of the gradient of g, it's going to have to be the case that 2 times our height of our box is equal to the width. That 2h is equal to w. You can also use the fact that these second and third equations are going to be equal to each other. We'll get 2 over L plus 1 over h equals 2 over w plus 1 over h. And what can we do with this? What can we do with this equality? Yeah?
Subtract the 1 over h from this one.
Cancel out a 1 over h. That'll give us 2 over L is 2 over w. And if 2 over L equals 2 over w, what can we say about the relationship between L and w? Mala?
Well, 2w equals 2l. W equals l.
There we get 2w equals 2l, which is the same as saying w equals l. So from these two equalities, we know something about the relationship between all our variables. That if we have one of these second types of critical points, we need that 2 times our height is equal to our width, and our width is going to be equal to the length. Just to let you know, if you set the first and third of these equal to each other, you're going to end up with L is equal to 2h, which is something we kind of already have from these other two equations. That width and length are going to be equal, and they're both going to be double the height of our box. So we have a problem. We'd like to be able to say, here's three single values for h, L, and w. We'd like to be able to say h equals this number, w equals this number, whichever one I didn't mention. I think L is equal to this number. Right now, though, this by itself doesn't allow us to come up with individual numbers for h, w, and L. So how can we use this information to plug into some equation maybe and solve for h and or w and or L? In particular, there's an equation on the board that we haven't used yet in this part at least, to say our constrained function f will have to have an h, L, and w at any critical point of these numbers. What equation can we use? Rob?
WL equals 4.
Yeah, we can use our constraint equation. And so if we plug these into our constraint equation, what we'll end up with is that if 4 is equal to h times L times w, we could say, well, L is equal to 2h. W is also going to be equal to 2h. So that we end up with that 4 is going to be equal to 4h cubed. If we simplify the right-hand side, 2 times 2 is 4, h times h times h is h cubed. How can we then solve this for h? What's going to end up having to happen here? Laurie? Okay. And h would have to be 1. If h is 1, Laurie, what are w and L going to be? Other way around. Well, we have that h is equal to 1. We know that w and L should both be equal to 2 times h. So if we plug in h equals 1 into this equation, what's that going to give us for w and L? Yeah, using the fact that 2h, w and L are both 2 times h, if h is 1, then w and L both have to be 2 times that in order to give us a value of 2. And so, in the end, we only find a single critical point this time that also happens to satisfy our constraint equation. Meaning h equals 1, w equals 2, L equals 2, that's the only set of values that's going to make the gradient of f a scalar multiple of the gradient of g, and that's also going to satisfy that h times L times w is going to come out to 4 cubic feet. How do we know that this is going to, do we know that this is going to be a minimum for our surface area function? That's a little bit tricky. We'd like to be able to say that this gives us a minimum. How do we know it can't give us a maximum? And here, I think you would have to, the best way to do that is to give some sort of intuitive argument, as in, I don't think, I'm going to write this back up on the board for surface area. Surface area was LW plus 2HW plus 2HL. I don't think that surface area is going to have a maximum subject to the constraint equation, because we could always do something like take, for instance, h is equal to 1,000, w is equal to 0.001, L equals 4, and then make surface area super, super huge just because of this 2HL term. We can make the surface area as big as we want just by making h really big and w really small. That's going to give us some super huge values for our surface area. And so it's going to turn out that this can't possibly be a maximum because our surface area function doesn't have a maximum, even subject to the constraint. And so this is going to give us a minimum value for the or values of h, w, and L that will minimize the surface area. If you want to look in the book actually gives like a procedure for telling you, oh, here is a Hessian matrix criteria going back to the decays from standard 13 way of telling you if you have a max or min. I don't want to spend like a full class to get into that formula again because it's messy and got other stuff I'd rather be doing, honestly. So for now, I think we can just come up with like an intuitive explanation for why does this have to be a minimum and not a max, even if we only have 1 point. By the way, what do we need to put on our h, w, and L before we can say we have a final answer for the dimensions of our box? You can't just say, oh, our box is going to have a height of 1, a width of 2, and a length of 2. What are we missing, Max? Yeah, we need to have units for what is our height, width, and length. And what are going to be our units for those 3 dimensions? Oh, why feet? Yeah. The fact that volume was given to us in cubic feet means that height, width, and length are all going to be given in feet. 1 foot height, 2 feet of width and length. So it turns out our box in the end is wider and longer than it is tall. Maybe it looks something like this. It's a little bit on the short side for a box, but that would be a way to maximize, or minimize surface area while still keeping it a volume of 4 cubic feet. So what do we do? We were given some information at the start about, oh, we have a rectangular box, here's what our constraint is that volume is 4 cubic feet, we want to minimize surface area. We came up with formulas for surface area and volume, based on which was helpful to draw a picture for that. Our constraint volume gave us our G, because that's the one that was a constraint. We knew what volume had to be for. And surface area was our F, because that was the thing we wanted to find extrema for. We wanted to minimize surface area. We then found all points satisfying these two conditions, as well as satisfying our constraint equation. Found only a single point that satisfied one of these two things. And that single point we then convinced ourselves was a minimum for surface area. This is a long, complicated problem. This is more than I would give you to do on a quiz. If this is a quiz question, I would probably only give you like part of this problem. Maybe like find formulas for F and G that we could apply the Lagrange multiplier method to, or maybe I would just give you formulas for G and F from the get-go and say, find the critical point of this. But this is kind of a long and complicated problem. But in the real world, this is the sort of process you would actually go through to answer this sort of question. If you were working for UPS and you wanted to minimize box surface area, the cost of producing the box, while keeping the volume constant, this is the sort of procedure you would have to actually go through. Any questions or comments about this process? Yes, Holly?
So if the first condition was packaged food, do you have to like try the second condition?
I would say you have to do both regardless. Because you could potentially have some points that satisfy condition 1, some points that satisfy condition 2, and if you do that, then you would have to like put them in a table, find out which one gives you biggest, which one gives you smallest. Sort of like the example we did, like we were doing in standard 13. If we had like where we had 3 different types of points where our extrema could be, you just plug them all into a table, see which is biggest, which is smallest, and then determine absolute maximum from there. So even if we had some points satisfying condition 1, that doesn't mean we couldn't also have points satisfying condition 2 that could give us our true minimum. Good question. I probably saw another hand. Any other questions? We've got a few minutes left. Let's work through one more really quick, just so you have another example to see in your notes. So the next one, not so bad. It's going to be find 3 numbers whose sum is 16 and whose product is as large as possible. Yeah?
The packet says 18.
So it does. I like 18 better because if we keep it as 16, it's not going to give us integer answers. Good catch. Dr. Gersel can't read his own typed out notes, apparently. So we want to find 3 numbers whose sum is 18 and whose product is as big as it possibly can be. So what's going to be our equations for a constraint and for the expression we want to maximize in this case? Eric?
You have the constraint, the x plus y plus z equals 18.
Okay. So you want to call x, y, and z. Makes as much sense as any for what to name the 3 numbers. And then what's going to be the expression we want to maximize then? So in other words, how would you write out the expression that gives you the product of all three? X times y times z. And the top one is going to be our constraint. So it's going to be our g. And the bottom one is the expression we're actually trying to optimize. So it's going to be our f. And so I think we can use these two functions to look for points. Where's our gradient? So first of all, we're a little low on time, so I'm going to work through this one kind of mostly on my own here. Gradient of g, to me, is going to look like 1, comma 1, comma 1. If you differentiate with respect to x, y, and z respectively, they're all going to come out to 1. Gradient of f looks like yz, xz, xy. Madeline, can you think of any points that we could plug into the gradient of g that would make this expression come out to 0? Now this is constant. It's always going to be 1, 1, 1, no matter what you plug into the gradient of g. So once again, we're not going to have any points satisfying our first condition, which is often the case, by the way, in looking at these problems. You've never picked up on that. So if we look at case number, so gradient of g equals 0 has no solution. So if we try and set gradient of f equal to lambda times gradient of g, I think we're going to end up with a system of equations. Yz equals lambda, xz equals lambda, and xy is equal to lambda. This one's nice. They're already written, or they are all already written as lambda equals a thing. We don't have to solve anything for lambda. If we were to set these equations equal to each other and get, for instance, yz is equal to xz, if yz is equal to xz, what's that going to tell us? Bob? Y equals x. Or z could be 0. Turns out we can eliminate the z equals 0 case, because if z is equal to 0, that would tell us lambda is 0, and if lambda is 0, then x or y is going to be 0, and if two of our three variables are 0, that's not going to maximize the product because the product would just come out to be 0 in that case. I'm not going to write that out because I'm running low on time. But basically, what we end up with is that y is equal to x. Using these two, we can find out that y is equal to z as well. So all three of our variables are equal. And then, once again, if we plug that back into the constraint equation, we'll get x plus x plus x, triple x, spicy, is equal to 18. And then we get a evil-looking answer. X, y, and z are 6, 6, and 6. And then we would convince ourselves this is a maximum because it's not a minimum because, well, it's bigger than 0 plus 0 plus 0, 0 times 18, for instance. Once again, Lagrange multipliers gave us a system of equations that we could solve that led us to this answer. All right, there's one more problem in the packet. I've also posted some practice problems in the book. Between now and Friday's quiz, I encourage you to try out a few practice problems for yourself, just to make sure you know you're comfortable with working through them. And then on Friday, after the quiz, we're going to start talking about integration. How to take integrals of multivariable functions. Have a good one, everybody.
I'm in number theory right now. Is it similar to that at all?
There are definitely some overlap in terms of like how you do write different types of proofs. How do you do something? How do you use like mathematical induction, for instance? Properties. Some of our examples involve things like properties of prime numbers. So there's it's a very similar course in flavor, but we'll be looking at different topics too, like that you're not going to be doing in number theory. How to do graph theory. How to look at how to do like a bunch of processes using recursion, how to do some set theory type stuff that I'm guessing you didn't talk about in numbers.
Not obvious. Okay.
So there's some overlap, but not, but it wouldn't be necessarily a waste of your time to take these three after numbers, I guess.
Yeah, I was worried about the other way around and like a waste of time to take number theory, but it seems like there's an application. So I'm thinking of doing that theory.
In that case, discrete would probably be a really good fit for you.
Okay.
And I think you would, after number theory, you'd be very well prepared to take discrete.
Alright. Thank you.
Oh, no problem.
See you on Friday.
Have a good one. Hello, Mal.
Next week, we're leaving for nationals, so we can have Tuesday, Wednesday, Thursday, Friday.
My
Well,
goodness.
That's still Wednesday or Friday, but.
That's on getting the nationals, first of all.
Yeah.
And second of all, yeah, no problem.
And then you post lectures and stuff, so okay, I'll make sure to watch.
Oh, speaking of which,